Okay, 6.3. This is where we're going to start our introduction to vectors. It is quite extensive and quite long, so I do apologize for that. But make sure you have your books out and open because you're going to fill in all of this kind of vocabulary word. And I'm going to kind of jump in and focus on what I really want you to know about this because it can get quite overwhelming and quite complicated. A vector has this beginning point and it goes on through a point. So this line segment, it has an initial point and it has a terminal point. When we talk about a vector, it has magnitude, which is also known as length. And it's denoted by this kind of double bar absolute value looking thing, but it does not represent necessarily an absolute value. This double barred means our magnitude of our vector. And our vector is going to have our initial point through our terminal point, and it has an arrow with a half arrow, and that's the symbol for our vector. Generally, we use small lowercase letters U, V, and W to mean that. When we look at a vector, we want it to have the same direction and length. So on example 1 here, in order to prove that the vector U is equal to the vector v, we have to prove the slope is equal to the distance. Now, you could draw a quick little picture of this, and you could get P00 to 32, so that's PQ. And then we have 1, 2, and 4, 4. And that's our RS. So that gives you kind of a pictorial of what we're looking at, and we want to prove that the U vector is equal to the V vector. And the way that we do that is we would prove the slope of the U is equal to the slope of the V vector, of which we should know how to do y minus y over x minus x. And then we're going to prove length, or the magnitude. And the way we prove magnitude or length is with the distance formula, where we know it's x minus x squared plus y minus y squared. So we would do the length of the U vector and the length of the V vector and prove that one equals the other. And I want you to complete that example. All right, on the second page, when we talk about our points of it, we use this terminology or this notation with arrows. And this is called component form. And we're going to be talking about another form here. So component is going to use these little arrows, and it talks about the difference between the initial and terminal points. That's how we get these V1 and V2. In your book, you can fill this in about the zero vector. The component of the vector, again, this is in your book. I want you to fill it in a little bit more completely than what I'm going to do right now. So component form is that V1, V2, which comes from, and that's what I want you to fill in here, the subtraction of the initial minus the terminal. And we do that for our x and y, and that's what gives us our final here. The magnitude, so here we have vector. Our magnitude, again, go to your book, fill this in a little bit more completely, but what I want you to sum it down to is I get the magnitude by taking the square root of my final 2 points squared and added together. So whatever this terminal minus initial, I wrote this backwards, it's terminal minus the initial, gives us my x point, and terminal minus initial gives me my y. Whatever those are squared and then square rooted is how I find the magnitude. Talk about the unit vector. We're going to do more with that a little bit later. On example number 2, where it says find the component form, so that means we're going to write it in these little arrows. And in order to find component form, we take terminal minus the initial. So I would take, if this is my initial, these are my terminal, then the component form is the x minus the x, the y minus the y, for the resultant of negative 512. So if I want to find the magnitude is to take those components and square them and add them together. And so I get the square root of negative 5 squared and 12 squared, which gives me the 169, which gives me 13. So that's the very quick abbreviated version of how to find component form and the magnitude. And we use this later on, but we do some much more complicated things with it. All right, 2 basic operations that we are going to do is going to be scalar multiplication and vector addition. And it's very, very similar to what we do with matrices. So I'm going to kind of skip a lot of this. Some of this is pretty straightforward. You're going to fill this in with your book. So when I do a note check, I expect to see this all filled in from your book. But basically, what it says is when we're doing the addition of them, we add corresponding pieces, which is pretty straightforward. And when we do a multiple of it, then we multiply the pieces. I mean, it's pretty straightforward. And the same thing happens when we do the negative of it. Basically, we distribute it. And when I subtract, I got to remember to subtract the second vector, so all the pieces of the second vector. So again, this is a lot that's in the book that I want you to go through and fill in. All right, on this back side, it says it wants you to find these different components, whether we're scalaring, adding, subtracting, and then it wants you to sketch what that would look like. So if I took 2 times v, that's 2 times negative 2, 5, I get negative 4, 10. So negative 2, 5 is my original vector of v. Now my final vector is then negative 4, 10, which is just the extension of it. But that's what a sketch would look like. Here I have w minus v, so I'm going to take the w and I'm going to subtract the v, x locations, and I'm going to do the same for the y locations and get a final resultant of 5, negative 1. If I look at this pictorially, I start with w, which is at 3, 4, so there's w. And I'm going to subtract v. So when I subtract the negative 2, that actually is to add. So there's my, I'm here and I'm going to take 2 steps. And then I'm going to subtract 5, and that's actual 5. So 1, 2, 3, 4, 5. So I'm down here. when I subtract a -2 and I subtract the 5. So that's my minus the v. So that's subtract v. I get the resultant down here of w minus v, which is 5, -1. v plus 2w. So first of all, I'm going to take 2 times the w and get 6, 8. And then I'm going to add it to the v so that I get the resultant of 4, 13. So when I do this, I would take v is -2, 5. This is just the pictorial version of it. I would add the 2w, so I'm going to add 6 and add 8. So add 6, 1, 2, 3, 4, 5, 6, and 8. 1, 2, 3, 4, 5, 6, 7, 8. So that there is my resultant, because here is, there we go. And my resultant is v plus 2w. All right. Oh, this was the add 2w. This was the v. All right, in your book, you can fill in these properties. They're pretty straightforward. The next we talk about is the unit vector. The unit vector is the vector divided by its magnitude, which if I pull out or kind of GCF out the vector, I can get 1 over the magnitude times the vector. That's the same thing. So in example 4, it says find the unit vector. So I need to find it by doing this process that we have up here. We know what our vector is. So I'm going to take -2, 5, which means I now can find its magnitude, because remember the magnitude is each of the pieces squared and added together, square rooted. So I get -2 squared and 5 squared. So I get -2, 5 over the square root of 29. Now I can separate this out and I can make it 1 over root 29 times the vector. But whenever I have it, I'm going to distribute it, so I don't need to undo to put it back together. So I can just distribute the division right away and get -2 root 29. And you can leave them ugly like this in 529. So this is actually the unit vector. The unit vector comes from taking the vector and dividing it by its magnitude. That's the unit vector. And we can prove this by doing the actual distance formula of the unit vector. If I do the distance formula of the unit vector, or the magnitude of the unit vector, same thing. If I square root each piece squared, well, that's going to give me 4 over 29 plus 5 over 29, which is 29 over 29, which is 1, the unit. So I can prove that, that it was the unit vector by putting it back into its magnitude setup. All right, this next thing is called our standard form. The standard form is another way to write what we've been doing. The difference is, so here's our component form. V1, arrows, comma, V2. Component form takes off the arrows, calls the first term I, adds the second term, and we call it J, lowercase I and J. And that is standard form. It takes off the arrows, and instead of a comma, it puts a plus sign. That is going to be our standard form. So let's look on page 6 here, example number 5. In this case, it says we have a vector with initial and terminal, but instead of putting it in our first form, we want to put it into the standard form. The process doesn't change. We still subtract the terminal minus the initial. So I would take terminal minus initial x value, sorry, that's -1 minus 2, and then the y, 3 minus a minus 5. And that gives us our component form, what we were doing originally. But if we want to change it to standard form, drop the arrows, put an I on the first one, plus sign, put a J on the second. Just changing forms of the exact same thing. I can add and subtract vectors, I can scalar them, and I don't have to do it in component form. I can do it in standard form, and we do this the exact same way they would do it if it was any other letters like x's and y's. So I would distribute the 2 to the u, and then I would distribute a -3 to the v, and then I would combine like terms. But I'm going to put the I part first, even though it does come alphabetically like the x and y would, but I always denotes the first component and the j denotes the second component. We can do all of this from a directional angle as well. If we know our vector has components x and y to it, we can now find the angles by putting it in our cosine and sine. That's our component form. We can also change it then to this new standard form. So cosine is I plus sine of j. We can change our component form to standard form for our cosine and sine as well. The angle is called the directional angle of the vector. So when we're looking at a picture here, here's my x, here's my y, here's my theta. Well, this x is really cosine, the y is really sine, and therefore my vector is u. See how here's my vector u? I can now use sine and cosine to help find that angle if I know a vector. And we're going to start off with finding the angle from the horizontal. We're going to look at how to find the angle between two vectors, but first of all we're going to start with how do you find the angle just between the vector and the horizontal. So in this case, 3i and 3j is the vector. Remember, that's our x and that's our y. So that's my vector u. What I'm trying to find then is that angle. From our last chapters, we found we can make a triangle. If I know opposite and adjacent, I know tangent. So tangent of my angle is opposite over adjacent. Tangent of angle is 1. So we hopefully know that that's 45 degrees. If not, use your calculator. Because like on the next one, we're going to have to use it because we don't know it exactly here. So here we have 3 minus 4, so there's 3. There's our -4, so there's our vector v. What we're trying to find is the angle. We know 3 and we know -4, so again we're going to use tangent, opposite over adjacent. We need to use our calculator at this point, and we're going to get a negative angle. And the reason for that is because this went in our horizontal, and our horizontal is below the x-axis. That is a negative angle. But whenever I find this, I do need to find the positive of it. So in this case, the positive is all the way around. And remember, a reference angle, and that's what we found here. The reference angle is the same as the other portion of it. So I would say 360, subtract that, and I would get my angle is 36.87 degrees, because you can't have a negative when we're talking about vectors. On page 7, again, this is from a horizontal. This one's a little bit easier because it tells us that from our horizontal it is 30 degrees. What works nicely with our 30 degrees, and we know the plane is moving at 100, is that with a 30-degree triangle, we know our pieces of information, because we know across from the 30 is half of the hypotenuse, and the other side is 50 root 3. Now just take care of our signs so that the component form, we're not finding an angle here, component form, we can have negatives. So component form is our x and our y. Example number 9, I'm going to leave, and I want to do that in class with you. And example number 10. This is talking about a plane that meets a headwind. So what is the velocity of the plane? What is the velocity of the wind? So here I have the plane is my vector 1 here. I know the plane is 30 degrees north of west, so I know that is 30 degrees. There's my plane. Therefore, I know that that's 60 degrees. I also know that my plane is going 500 per hour, which means I can also find my other components. I know my x component, which is across from the 30, is 250. Therefore, 60 is 250 root 3. Now, this wind is pushing my plane. So the velocity of the wind, let me go back and finish here. So I know component form of the plane is negative 250 and 250 root 3. All right, so now when I go to the wind, it tells me is at a direction of north 45 degrees east. So north tells me that's 45, which means this is 45. And I should know that of 45's, if it's at 70, that it's root 2 over 2 of that. It's 75 root 2 over 2, which makes it 35 root 2. This is root 2 over 2 times 70 for the same thing, 35 root 2. So I know the velocity of the wind is 35 root 2, 35 root 2. Now, together, the plane and the wind, the total is going to be the plane and the wind. And when I put those together, I'm going to use decimals because I'm now in a real world problem. Negative 250 plus the 35 root 2, I get negative 200.5. And then the same thing, the plane and the wind. When I add that together with decimals, I get 42.5. So that's just the vector of my components. The speed of the plane is the magnitude. Well, the magnitude is the square root of those pieces squared. So the speed and the magnitude then is 522.5 miles per hour. So that's the speed of the plane. And now we can find the angle that it comes at, because it says what's the resultant speed and the direction of the airplane. So we can find the resultant speed of the magnitude. Now we need to find the direction. The direction is going to be tangent, because we know our opposite, our y, and we know our adjacent, which is our x. So tangent of my angle is the y over the x. Remember, you're going to do inverse tangent here. And you're going to get a negative degree, but that can't happen. Can't have the negative. And since the negative is in quadrant 2, we're going to subtract or add 180, however you want to think about it, to get 112.6 degrees. Okay, and that's going to be 6.3.